Greetings. Ring is an algebraic structure with the following properties. The first property is basically the idea that a ring is a set, usually denoted R due to the first letter of the word ring, with two operations, addition and multiplication. And these operations have to fulfill some connection to this set. These are just following, I'll just talk about them now. So basically, the set R, it contains all the elements of the ring, then we have these two operations, plus and multiplication sign, therefore these operations are called multiplication and addition and multiplication. But the point is, they don't necessarily have to mean addition and multiplication in their most basic arithmetic sense. They can be also slightly different operations. This is arbitrary name given to them. Alright, now the first point, and probably the first of the usually mentioned properties for rings, is that the set R, only with the addition operation, is a commutative group. So R and multiplication is a group, and it is commutative. So with just this operation, the set R is a commutative group. And what this means is basically that and this will all apply for AB inside R, alright? So for some two elements, for any two elements AB inside R, it applies all these things, that A plus B equals B plus A due to the commutativity. Also, there exists something like an inverse of A, usually that is denoted as A to the minus 1, but in the case of rings, denoted usually as minus A, simply. There exists minus A inside R, and minus A plus A. And due to the commutativity, this could also be switched, equals 0. And of course, there exists 0 in R, and this is the usual denoted as E, but in this case, again, a more intuitive sense, it is denoted as 0. There is a 0 inside R, so that for any element A, when it's in this addition operation with 0, it still is the A. So there's identity element, there's always inverse for any element, there's commutativity as well, and there's also associativity. So well, I'll add this again because there's another C here. So A plus B plus C, where the parentheses are here, equals A plus B plus C as follows. So these are the first few properties connected to it being a commutative group. And now the next properties are alongside the multiplication operation. So all these things have been taken into account in the context of addition. What we've said is the set R only with the addition operation is a commutative group, but with the multiplication that has not been mentioned, it actually is not necessarily, it's not so. The requirement is different for the other operation, and it's actually more less constraining, one could say. So with the multiplication, what has to be satisfied is basically the following thing. The multiplication does not even have to be commutative, first of all. So multiplication doesn't have to be commutative. And what has to be satisfied nevertheless is there exists, so this is for the fact that A and R and plus are together a commutative group, but this will now apply for the multiplication relationship with R. So for the second operation, multiplication, there exists some identity elements for multiplication. Just like here it was called 0, now it will be called 1. And it exists inside the R set. And what it means is there is some A times 1 equals still A. So this is basically the identity element for R alongside multiplication. And then also multiplication has another property. It's also got associativity. So even though it's not necessarily commutative, it has associativity. That means A times B times C inside the parentheses is the same like A times B inside parentheses times the C outside, where the multiplication is among all these three elements. Now, also this is for any three elements A, B, C in R. Alright. This is connected to this. So this is for the multiplication, and then there's another property that connects the multiplication and addition together slightly. So I'll delete this so far, and we'll go over the last part of the requirements, and that is that basically multiplication is distributive over addition. So when we have a times b plus c, it will equal to a times b plus c plus a times c, and if I switch this b plus c times a on the outside here, then this element, it will follow the usual rules as one would expect. So multiplication operation is distributive over the addition operation. A times b plus c is a times b plus a times c. B plus c times a is b times a plus c times a. So this is the distributive addition on property. And basically these are the requirements, and they've been basically fulfilled by many common sets, big sets that are popular in mathematics. And these are, for example, examples of a ring is the set of integers, is the real numbers, the complex numbers, and so on. There's many examples of rings, even other sets that are not so big like these ones, but namely these three probably the most famous ones. They are all rings. If one thinks about it, they fulfill these properties. And what's good about rings, for example, one concrete thing that one could take and compare them through with groups is, for example, they don't necessarily require an inverse element for the multiplication operation. So that basically makes them a little more of a wide scope. And of course, there's more concrete types of rings that one could go into. We're going to go into them in next videos. But in general, a ring by itself, without being, let's say there's idea of a commutative ring and so on, or with non-zero inverses for multiplication and so on, then we will go over that in the next one, and we'll slightly and start connecting actually to the idea of the algebraic structures of fields.